So I appreciate it. Right, so if you have two sequences, they both converge, the terms of an are less than or equal to bn, then what do you think you should be able to conclude about their limits? And here I call for a strict less than. I think they could, because an and bn could be the same sequence. And there will be a tangential interjection a little bit later asking what happens if you try to put some strict inequalities in here. So there's one. And the other result I'm going to prove in the next couple of minutes is the squeeze theorem. If an is less than or equal to bn is less than or equal to cn, and an converges to a and cn converges to a, then, yeah.
Good question. Why does it make for sequence to be less than those sequence?
Oh, cool. So let's just read that whole statement. For every natural number n, an is just a natural number, and bn is just a natural number. So it just means each term of an is less than or equal to the corresponding term of bn. And sometimes you will see someone write just like an less than or equal to bn less than or equal to cn. Chances are that when you see that written down, they'll mean for every natural number. But here I think I've actually included the quantification for all n and n. Does that answer? Okay, excellent, excellent. So squeeze theorem, an less than or equal to bn less than or equal to cn. An and bn both converge to b, both converge to a number a. What can you tell me about bn? Also converges to a. And all right, that's the squeeze theorem you remember from Calc 1, right? I guess it's for sequences and not functions, but. So let's prove these two results. Novelly enough, I will prove them in order. So the first result, I want to prove a is less than or equal to b. And I get to assume lots of things about limits of sequences. I get to assume a n converges to a and b n converges to b. Both of those statements tell me something is true once I have a positive number, an epsilon. In order to get an epsilon into play, let's appeal to this theorem 2.2.10, the thing that says a is less than or equal to b if and only if you have a strict inequality for every epsilon bigger than 0. And let's try to do that. To prove the first result, we will show that for every epsilon bigger than 0, you only need one of those two that's, and I don't care which one, but you don't want both of them. Just grammatically, it's bad. I'm going to show that a is less than b plus epsilon for every positive number epsilon. We've proven that that's equivalent to a is less than or equal to b. Or you did in homework. And I don't think I had any big objections on anyone's that homework. So we have this theorem. Let's use it. By theorem 2.2.10, we will then be able to conclude that a is less than or equal to b, the thing that we want. So if you like, this is like the lead-up sentences where you're explaining the logic we're going to use. This isn't going to be quite a direct proof. All right, so let's give all the assumptions. Let an and bn be sequences. Let's assume that an is less than or equal to bn for every n and n, that an converges to a and bn converges to b. I want to prove this thing about every epsilon bigger than 0, so let's consider any epsilon bigger than 0. Feel good so far? All right. Now let's just see what we get. I have this positive number epsilon, and I know that an converges to a. What does the definition of the limit tell us then? I have an converging to a, and I've already picked a positive number epsilon. So I've already picked a positive number epsilon. So there must exist some big N corresponding to that epsilon. I'll call it big N1 because I'm about to do the same thing for the sequence Bn. Such that as soon as for all, the definition of this concludes there exists some big N so that for all little n bigger than big N1, absolute value An minus A is less than epsilon. Does that actually follow? Could I do the same thing for Bn? Yeah. Similarly, there exists a Bn so that there exists some N2 so that for all little n bigger than big N2, absolute value Bn minus B is less than epsilon. So far I've just like unpackaged definitions. And even if you have no idea what to do, unpackaging definitions is often useful. So let's see what we can do with that. Maybe we'll draw a picture. So here's my goal, is that A is less than or equal to B. Oh, yeah. And I've translated that goal to A strictly less than B plus epsilon. So if I could like find some things that live strictly in between A and B plus epsilon, that would accomplish the goal. So let's try to do that. Let's just try to get these inequalities that we have into some inequalities that just have An and Bn. And this is, I think, going to be like a scratch walk off to the side. What do you get if you like go and solve that for A? Well, all right, let's, I guess, do it one step at a time. Let's get rid of the absolute values first. If a thing is less than epsilon, that means that that thing has to be between minus epsilon and plus epsilon. And that was like one of these properties of absolute value that maybe we did, maybe we didn't prove. If you want to solve this for A, well, solve that for A, just do it. What do you get?
Minus epsilon is less than A, is less than A and plus epsilon.
Like that? Could I do the same thing for the B's?
Yes.
Yeah, and I think I don't even want to do the same walk again. And so this is like me gathering some facts together. And I also know that An is less than or equal to Bn. Gesundheit. So each of these only have to when little n is big. This happens for every little n. And I'd like to know something about the relationship between A and B. Let's say I know A is less than An plus epsilon. And I eventually like A to be less than something. So I think this is useful. And An is less than or equal to Bn. Cool. Could I do something here to maybe get Bn plus epsilon to be less than something? Well, that inequality goes the wrong way. I want Bn plus epsilon to be less than.
Oh, yeah.
Could I just like add 2 epsilon to both of these? Would that do the job? Yeah, let's do that. Oh, neat. Does this give me the result that A is less than B plus epsilon? I mean, almost. There's a 2 epsilon instead of an epsilon, but I got to choose epsilon. But we have like a trick. I could do all this for any positive number. What would you like to replace that epsilon by? Epsilon over 2. This is like the epsilon over 2 trick. And a lot of times when you're reading like an analysis paper where they're doing this, they'll do all this work and they'll get that this is less than or equal to like 538 epsilon. And then they'll just say, then this completes the proof by dividing epsilon by 538. We won't do that. Instead, we'll divide right now. So instead, since epsilon over 2 is bigger than 0, I can divide those 2 by 2. And now we know everything we need. So first of all, let's let big N be the max between those 2 big N's. Let's let little n be bigger than big N. And since an is bigger than a, then an minus an absolute value is less than epsilon over 2. So that a, and this like algebra scratch work I don't need to see. Because right, like I know what you're going to do. You're going to rewrite that as it's between minus epsilon and plus epsilon. Then you're going to add epsilon over 2 to both sides. A is less than an plus epsilon over 2. That seem okay so far? All right. Similarly, since little n is bigger than big N over 2, B is less than right, like that's what we actually used. That B is bigger than. Feel okay so far? And now let's gather these things together. So let's put this all together. I know that an is less than or equal to an plus epsilon over 2. Is less than or equal to bn plus epsilon over 2. Feel okay so far? I think I want a sentence interjected. Because I want this to be less than, I want a bn plus epsilon over 2 to show up. So how could you rewrite this so that bn plus epsilon over 2 is less than something? Or like, what did we do in the scratch walk? We like added something to both sides? Let's add epsilon over 2. Adding epsilon over 2. Nope, not epsilon over 2, straight up epsilon to this. We get b plus epsilon strictly bigger than bn plus epsilon over 2. There we go. All right, so now we have an strictly less than an plus epsilon over 2. That's less than or equal to bn plus epsilon over 2 since an is less than or equal to bn. And we have that that is less than b plus epsilon by the thing that is just written in red. And so, comma, and there should be a white space there too. A is less than b plus epsilon. We've now proven that that's true for every epsilon bigger than 0, so a is less than or equal to b. But how did that feel? that each step seemed internally consistent at least. Each step followed from what came before. And there was this bit of logic where like this theorem 2.1.10, that big fancy theorem got used. And I cited it by name and also by number. I cited it's the theorem that says that A is less than B if and only if A is less than or equal to B plus epsilon for every epsilon bigger than 0. And that's not like, it's a theorem that's really important to anything else, but it's not a theorem that has an A. And oftentimes you'll be reading a math paper, so it's not something to cite for that theorem outside of like this class, so pointing to that theorem in this textbook. You'll just do it. You'll say, instead, I'm going to prove that A is less than B plus epsilon for every epsilon bigger than 0. All right. Squeeze theorem. So let's start with an incorrect proof, because I think it's valuable to see an incorrect proof, and you'll tell me what's wrong with it. So let's start by remembering what the squeeze theorem says. The squeeze theorem says if AN is less than or equal to BN is less than or equal to CN for every N, and AN converges to A, and CN converges to A, then Bn also converges to A. So there's the statement of the squeeze theorem. Let's now go through this proof that I'll tell you in advance is incorrect. Let's suppose An, Bn, and Cn are sequences. Let's assume that for every natural number n, An is less than or equal to Bn is less than or equal to Cn. Let's assume that An converges to A and Cn converges to A. So far, any issues? All right. If B is the limit of Bn, then we see from part 1 that A is less than or equal to B is less than or equal to A, so B equals A. Any issues so far? Thus, Bn converges to A as we claimed.
Is the issue that you're assuming that
Bn conversion isn't an assumption of the theorem, it's a consequence of the theorem. So, if you wanted to use this proof, you would need one more step. So the theorem concludes that Bn converges. We've just assumed that Bn converges. So one thing you could do is, like, we will be done if we can show Bn converges. So it's one thing you could do here. This isn't what we will do. You could fix this proof by saying, well, let's suppose that Bn does not converge and get a contradiction. And you should be able to do that, right, because the theorem is true. But this is a sneaky mistake. Don't assume that something converges unless you already know it converges. Or you can assume for now it converges and deal with that issue later. I suppose this does show one thing. This shows that the only thing that Bn could possibly converge to is A. It doesn't show that it converges though. So here's an alternate, just straight up direct proof. Let's suppose that An, Bn, and Cn are sequences, that for all n, An less than or equal to Bn less than or equal to Cn, that An converges to A and Cn converges to A. I know what I want to show. I want to show Bn converges to A. So, epsilon n definition says that what do we then need to show? We need to show that for every epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, absolute value Bn minus A is less than epsilon. That's what we want to show. So let's just continue on with this scratch walk. So we want to show Bn minus A is less than minus epsilon and bigger than plus epsilon. And the stuff down there isn't going to be part of the proof that you would eventually present. Well, let's walk with that. Let's just try to get some inequalities that involve Bn minus A. Do I know something that's automatically less than or equal to Bn? An. So let's stick an A in there. And I could do the same thing on the other side with Cn. Ooh, wait. Do you think I could show that An minus A is bigger than minus epsilon? Yeah, so let's see, absolute value An minus A. I know I can get this to be less than epsilon. Well, that means minus epsilon would be less than An minus A less than epsilon. Oh, neat. Does this look like it's going to turn into a proof soon? I think here's a bit of logic. So use An converging to A and Bn converging to B to say that there exists some big N, so this sort of statement is true. Solve it to get something like that. Do the same thing on the Cn side. Consider any little n bigger than those big N's. Well, Bn minus A is automatically between these two. Hey, our Cn. Yeah, great, okay, good. Whew. Which, and in turn, I could get that to be less than epsilon by the same logic. So let's now just try to do that. So we consider any epsilon bigger than 0, because we have to if we want to prove this sort of claim. Now I'll come up with my big N's, and I'll use An and Cn to do it. Since An goes to A and Cn goes to A, it follows that there exists a single big N, so that for all little n bigger than big N, absolute value An minus A is less than epsilon, and absolute value Cn minus A is less than epsilon. So in the past couple of proofs, I said, like, there's some big N1 so that 1 happens, so that there's some big N2 so that the other one happens, so that big N be the max. You'll notice that I'm, like, shortcutting all of that and just saying there exists a big N. But I think that's the stuff that's worth summarizing. Nice. So let's see what happens as a consequence. And you know what? Just because the scratch walk went this way, let's not put an An there. Let's put an An minus A and a Cn minus A in place. Maybe this is somewhat dangerous. So if An minus A in absolute value is less than epsilon, then what can I sandwich An minus A between? Awesome. Same thing with Cn. And combining this with the inequality An is less than or equal to Bn is less than or equal to Cn, which is an assumption of the theorem. I think I can say that Bn minus A is less than or equal to Cn minus A, bigger than or equal to An minus A. And now let's use the preceding lines. What's something helpful that I know for a fact is less than An minus A? Negative epsilon. Could I also put a positive epsilon on the other end? Does that give us that Bn minus A is less than epsilon in absolute value? Yeah, and like, there's really this theorem about absolute values that we prove that it's getting used there. But especially as we progress again, like these really early results, we won't cite those theorems. Neato. So that means that Bn minus A is less than epsilon, at least as long as little n is bigger than big N. And I decided that that was worth adding in, or it's probably not that important because you can look back through the proof and see that it's just for all little n bigger than big N. So let's just verify that we do this. Early in the proof, do we consider any epsilon bigger than 0? Do we consider any big N? Nope. Do we come up with a big N? Do we show that something is true for all little n bigger than big N? And is that something, this inequality? Oh, nice. So Bn converges to A. So there was like short, quickie proof that was trying to just use the previous thing and get a consequence, but it had a secret assumption. So instead we just came up with a proof right from the definition, a direct proof. Feel okay? All right. So that concludes the 2 sections that I handed out earlier. A little bit ago, I handed out the rest of chapter 3, starting in section 3.3. Everyone have a copy of it? Anyone like to use theirs in the meantime? Okay, that's good, because I don't really have an extra. I give you this one and then just walk on the board. Pretty consistently, when I do that, I have a better time, and the students have a worse time. So, let's start with this as motivation. This isn't in the notes. So tell me this. What's the limit? Just try to think back to like Calc 1. What's the limit as n goes to infinity of 1 plus 1 over n raised to the nth power? Not 1. So it turns out Euler's number E is defined to be the limit of 1 plus 1 over n raised to the nth power. So the answer is E. And then all of the things that are true about like e to the x follow from that fact. But there's a problem there. Is it obvious that that limit even exists? I mean, it's not, right? And if the limit is supposed to be e and e is defined to be that, then we're in trouble. Because we can't like come up with an epsilon n argument. Because we don't, like, e is defined to be the limit. So if we want to say let e be the limit of this thing, then try to come up with an epsilon n argument, like we just assume what we need to show. So something powerful in analysis is you can often write down limits that converge to numbers that you don't already know exist. And then you can prove that these limits converge by doing something abstract. And then you know that the limit exists, so you can do stuff with the limit. This is exactly what we'll do here. These big convergence theorems are theorems that tell you that some things converge. And maybe we'll bring this together. So we say that limit of xn is equal to L if, for every epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, epsilon value xn minus L is less than epsilon. And to use that to prove that something converges, like to prove a limit law, we needed to know what the limit should be before we got started. And if I asked you to do that for like this sequence, you don't already know what the limit is. Like it's like 2.71-ish, but that's not good enough. Right? Limits are exact values. So if you want to use this to prove that what a limit is, you need to start with a guess as to what the limit is, and then you prove that your guess is correct. Right? That's what our past couple things have been. Like the proof of the squeeze theorem was that. We knew that the limit should be A. Then we proved that the limit is A. But that's like a shortcoming, because sometimes you don't already know what the limit should be. Here's a thing that lets you fix that issue. Let's let AN be any bounded monotone sequence. I've underlined this because we don't know what that word means yet. Then AN converges. So this says that if you know that a sequence is bounded and monotone, it converges. So notice you don't need to know what the limit is to use this. You can just show that a sequence is bounded and monotone, then you'll automatically know that its limit exists. In fact, the homework for today, well, it'll probably be the homework for like tomorrow or maybe Friday, depending on what happens on Wednesday. Tomorrow doesn't exist. Wednesday or Friday. We'll have you go through an exercise in the textbook which explains why this limit exists. And it's going to have you fill in all the gaps you need to follow the argument in the textbook. And that's all that this is. It's having you read a particular page in Corkwood and fill in the details. But I think I'm getting past myself. I haven't explained what monotone means. And there are two other big theorems that we will prove later once we have a few more wards. Let's let AN be a sequence. Then AN converges if and only if AN satisfies some condition that we'll define later called Cauchy. And then the last of these big three convergence theorems that, again, I won't prove for quite a while. We're on chapter 3, right? This is in chapter 5. The convergence subsequence theorem. Let AN be a bounded sequence, then AN has a subsequence that converges. And I haven't defined what a subsequence means. But maybe the notation gives you an idea of what I mean by a subsequence. Nice. The underlying thoughts, they're not defined. Maybe in order to motivate why you need a word like monotone in monotone convergence theorem, let's just start by remembering this. So here's a proposition that we proved last time. If a sequence is convergent, then that sequence is bounded. Do you remember proving that? We did. The converse. Is the converse to that proposition true? If a sequence is bounded, then does it follow that that sequence converges? When you come up with a bounded sequence, so a sequence that just doesn't get huge, that also does not converge, that doesn't have a limit. And there's like a possible counterexample in there, right? Tell me about the sequence -1 to the n. Is it bounded? Yeah, right. What's the biggest it can ever be? What's the least it can ever be? So it's bounded below by -1, above by 1. Does it converge? No, because it like keeps bouncing between -1 and 1. So like, the limit wants to be 1 and wants to be -1. Can't be both. So -1 to the n is bounded by -1 and 1. Not that you actually care about what the bounds are for this illustration, but -1 to the n converges. So tell me, is the converse to 3.2.3 true? If a sequence is bounded, then does it have to converge? Nope. So the converse to 3.2.3 is false. But a version of it is true. If a sequence is bounded and something else, then it converges. And that something else is the word monotone. And let's define that. In fact, probably all of you have heard the word monotone at some point. Anyone have a memory of the word monotone? Yeah, in math. Not like my voice is. So let's give it. So I'll jump right down to the third sentence there. A sequence is called monotone if it is either a decreasing sequence or an increasing sequence. So a sequence is monotone if it's either decreasing or increasing. I bet you all know what an increasing sequence should mean. So if you follow your, well, let's write down the definition and then I'll say it later. A sequence xn is called increasing if for every natural number n less than m, it holds that xn blank xm. That's not really the intuitive choice. It turns out, just in order to make it more useful, we'll put a less than or equal to. So I'll allow sequences to be increasing even if they're like constant sometimes. And that doesn't seem so bad. Being constant isn't going to screw with the limit. What should it mean to be decreasing?
Term is less than subsequent, so greater than equal to.
Nice. And I like that sentence, greater than the subsequent. That's an easier thing to check than the definition of monotonicity right here. This is an important definition. What you just said is like a feeling, which we'll give in a moment. If you ever do want to put like strict inequalities there, say the word strictly. A sequence is strictly increasing if for every n less than m, xn is strictly less than xm. So what you just said is a sequence is decreasing if each thing is greater than or equal to, less than or equal to the subsequent term. Let's prove that. Well, maybe prove that. I have 8 minutes. Yeah, that's enough time to prove this. That's a silly typo, sequence, an is increasing if and only if ak is less than or equal to ak plus 1 for every natural number k. Does that agree with what you said about subsequentness? Yeah. Is this like something that seems like it should obviously be true? Yeah, I bet. In order to come up with a proof, well, one of the directions will be like obvious. The other one will use induction. And I think it'll be useful to see this using induction. So let's let an be a sequence. If I want to take the forward direction, I guess I need to assume Chris, let's assume that an is increasing. And let's just write down what that means. A sequence is increasing. So what does that mean? That means that for all n less than m in n, an less than or equal to am. And now I want to show ak is less than or equal to ak plus 1 for all k in k. That looks like a universally quantified statement. Let's consider any natural number k. I want to show ak is less than or equal to ak plus 1. Why should that be true?
Because the m is greater than n in that case.
Yeah, so since k is less than k plus 1 and an is increasing, a sub this should be less than or equal to a sub that. I have something that's true for every natural number. K and k plus 1 are certainly natural numbers. Cool. So ultimately, there were some sentences of setup, but the actual sentence where we did the proof was like 1 sentence long. Sometimes proofs are that way. The other way I think will be more interesting. So let's assume that ak is less than or equal to ak plus 1 for every natural number k. So let's think about what we need to prove now. So we want to show for every m, n, and m, if m is bigger than n, then am is bigger than or equal to an. That's what we need to show if we want to show the sucker is increasing. Here's one way of organizing these thoughts. Let's induct on the number little m. So, we'll proceed by induction on m. The smallest thing that's bigger than little n is little n plus 1. So let's assume that m is equal to n plus 1. Then, am, do some work, bigger than or equal to an. Why should that happen?
AM would equal a sub n plus 1.
Cool, I like that. Is that just bigger than or equal to an by assumption? All right, inductive step. So let's fix a natural number n, bigger than n. Let's assume that am is bigger than or equal bigger than or equal to a. Do you agree that is what the inductive step needs to do? Excellent. Cool. And like, here I think it's really important that you write down the sense of exactly what is the inductive assumption. Okay, so explain to me why that's true. Why should am plus 1 be bigger than or equal to an? Cool. And since there are two assumptions, maybe this time I'll write down what the assumption is, since ak plus 1 bigger than or equal to ak for all k. So you've just taken k equal to m. All right, what next? Yeah, by the, maybe I'll even call that the inductive assumption. Oh, so together those two just like do the job? Yeah, I guess like the fancy word to use now is transitivity. So by transitivity, am plus 1 bigger than or equal to an. And now let's just close with the magic words that make induction on. So we used induction, so by the principle of mathematical induction, you now see that for every little n bigger than big N, an is bigger than or equal to an, so the sequence is increased. Cool. Does that seem all right? And I want to argue that what we just did was to some extent more like an algebra or discrete math proof. I don't think there's a whole lot of analysis in this. Starting out on next time, depending on if people want to ask me questions, or on Friday, we'll start doing some analysis because we need to prove the monotone convergence theorem. I notice it's got this fancy word supremum in it. Yeah. All right. Well, I'm at time, right? Yeah, I have less than a minute left. I'm comfortable calling this time. Yeah, 15 seconds.
So 15 seconds to the lecture. Just a whole new concept.
I don't know that I could prove the monotone convergence theorem in an intelligible way in 15 seconds.
Yeah, it's a timed exam.
15-second timed exam. Yeah. And make sure to come with questions on Wednesday, or else I'll just start lecturing off.